Señoras y señores, a continuación tenemos la conferencia del profesor Cohen-Tannoudji, del cual voy a hacer una breve presentación. Nuestro primer conferenciante es el profesor Claude Cohen-Tannoudji, de los Cohen de Tánger, familia que abandonó España en el siglo XVI huyendo de la Inquisición. Alumno de l'École Normale Supérieure, fue convertido al cultivo de la física por Alfred Kastler, Nobel de Física en 1966, y padre de Daniel Kastler, viejo conocido de quien os habla. Estudió mecánica cuántica con Albert Messier. Sus trabajos en el campo de la óptica cuántica son numerosos y fundamentales. Aplicando el atrapamiento poblacional coherente al enfriamiento por láser, consiguió con su grupo exhibir un nuevo esquema de enfriamiento sin límite inferior a la temperatura, que abrió el rango de los microkelvin y nanokelvin para congelar a los átomos con fuentes de luz y así hacer posible la creación de un maravilloso nuevo estado de la materia, los condensados atómicos Bose-Einstein. For development of methods to cool and trap atoms with laser light, fue galardonado con el premio Nobel en 1997 junto con Stephen Chu de Stanford y William Phillips del NIST.
Forward, backward. Thank you very much, Professor Galindo, for your very kind introduction. And let me also, before starting, express my deep gratitude to Professor Pedro Echenique for inviting me to give this opening lecture. This is a very great honor for me to talk about the great achievement of Albert Einstein and how he contributed to change our perception of the world. What I would like to discuss today is the Bose-Einstein condensation. In fact, during the last few decades, there have been great advances in the manipulation of atoms. We know now how to trap atoms, how to cool them with laser light and with evaporation, and it's possible now to reach extremely low temperatures in the nanokelvin range. In fact, the cold atoms we are now able to produce in the lab are the coldest matter in the universe. They are about several million times colder than interstellar space. At this temperature, new physical phenomena appear. You know, the atomic system is not just completely frozen. It exhibits new, fascinating, unexpected properties, like, for example, superfluidity. And to understand these properties, we need a purely quantum description, such as the wave-particle duality, quantum statistics, and what we have now in the lab are macroscopic matter waves, which constitute a new form of matter, a new state of matter. Just in this slide, I've given a few temperatures in the scale in Kelvin units, that in logarithmic scale. For example, here, in Kelvin units, the lowest possible temperature is 0. The room temperature here today is about 300 Kelvin. And for example, here you have the sun surface at about 5,000 degree Kelvin. The boiling water is about 373 Kelvin. The freezing water is 273 Kelvin. Here the atmosphere of Titan. This is liquid nitrogen. Around 2-3 Kelvin you have the superfluid, superconductors. And in fact, the cosmic background radiation, which fills the whole universe, is at 2.7 degree Kelvin. It's a remnant of the Big Bang. And now with the laser cooling technique and the evaporative cooling, we can go down up to the nano-Kelvin range, where we have the field of ultra-cold quantum gases. You see, we have a big step between this temperature and the temperature we know how to do. What are the basic techniques used to produce this state of matter? First, we have to trap the atom by magnetic field gradient or laser intensity gradient or combination of both in order to isolate the atoms from the hot walls of the cell which contains them. Then you have, of course, to work at a very high vacuum because you have to avoid any collisions with residual hot gases. Of course, you need also to have a very dilute gases because at these extremely low temperatures, usually the state of matter is solid or liquid. But in order to have a liquid, you have first to have molecules, and when two atoms colliding, they cannot form a molecule except if you have a third partner taking the energy. So you need to have three-body collision to form molecules from a gas. If you have a very cold gas and very dilute system, these three-body collisions are very rare, and you avoid the formation of molecules, the formation of aggregates, and you can maintain the gas in a metastable state which lives for a long time. That's an important point. And finally, you have to cool the system by using exchange of momentum between atoms and photons. And this is where Einstein has played a very important role. Because let me first remind you briefly what is light. Light, of course, is a wave formed by an electric and magnetic field oscillating in space and propagating at a very high velocity, which is about 300,000 kilometers per second. As any wave, light gives rise to interference and diffraction effect. But we know since the basic work of Einstein in 1905, which was really revolutionary because nobody was accepting his idea, we know now that light consists also of energy grains, energy quanta, which are called now photons. And these photons, if you consider the photons which are associated with a light wave with frequency nu, have an energy equals h nu, where h is the Planck constant having this value. And Einstein showed also in 1917 that these energy grains of light have also a momentum, P equals h nu over c. And of course, these two aspects of light are necessary. They cannot be dissociated. They are both essential, and this is what is called wave-particle duality. Now, what are the elementary interaction processes between atoms and light? They consist of two basic processes, emission and absorption. Emission, you have an atom in an excited state, E. It can fall to the ground to a lower state, G, by emitting a photon h nu. That's an emission process. The reverse process also exists. the atom can go from G to E by absorbing a photon h nu. And we have the basic relation. The difference of energy between the two states, the two energy states, is equal to h nu, because when the atom emits a photon, the energy that is lost when it goes from E to G is carried away by the photon. And when it goes from G to E, it needs some energy which is given by the photon. So that conservation of energy. And that can explain all atomic spectra. But what is important too is that you have also conservation of momentum. And I would like now to enter into this in more detail. And conservation of momentum is at the origin of an important effect which is called recoil. You have all seen, for example, a tennis racket hit by a ball, the racket recoils. When you have an atom in the lower state, G, excited by a photon with momentum h nu over c, when the atom absorbs the photon and goes to E, it recoils. Because of the conservation of momentum, exactly as the tennis racket. And the momentum of the photon, incoming photon, h nu over c, is given to the atom, which recoils with the velocity given by this equation, mv recoil equals h nu over c. So when the atom is in excited state, in fact, atomic excited state does not last forever. It cannot remain in the excited state forever. After a certain time, which is called the lifetime of the excited state, the atom goes back to the ground state, G, by emitting a photon spontaneously in all possible directions. And the lifetime of the excited state is typically on the order of 10 to the minus 8 seconds, 10 nanoseconds. And the properties of spontaneous emission are such that the probability of emitting a photon in two opposite directions are equal. So on the average, the loss of momentum due to spontaneous emission is equal to 0. So it's not 0 at the absorption, it's 0 at the emission. So if I consider a cycle, absorption followed by spontaneous emission, the mean velocity change of the atom, delta V, is equal to V recoil h nu over mc, due only to the absorption process. And if you put the number in this equation, you find that the recoil velocity of an atom absorbing and emitting light is typically on the order of 1 centimeter per second, which is very slow compared to the velocity of the molecules in the air around us, which are mostly about several hundred meters per second, even kilometers per second. Now, if you have an atom in a resonant laser beam, after a cycle, absorption emission is still in the laser beam. It can undergo a second cycle, a third cycle, and etc. So, and the mean number of cycles per second, since the duration of a cycle is determined by the lifetime of the excited state, that's minus 8 seconds, that means that the order of magnitude of the number of cycles per second is 10 to the 8, 100 million cycles per second. And now we can calculate the mean velocity change per second of the atom, which is, in physics, the velocity change per second is what is called acceleration or deceleration. So the mean acceleration A or deceleration, which is the velocity change per second, is equal to the velocity change per cycle times the number of cycles per second, which is V recoil times 1 over tau r. V recoil is on the order of 10 to the minus 2 meters. 1 over tau r is 10 to the 8 per second. So we get something which is on the order of 10 to the 6 meter per second square. And you know, of course, that the gravity, the acceleration due to gravity is 10 meters per second square. That means that an atom in a resonant laser beam feels an acceleration or deceleration 10 to the 5 g, which is huge. And that is called radiation pressure, a huge radiation pressure force. And using this force, which is huge, you can change the velocity of the atom. If you have an atom going that way, and the laser beam going that way, you can stop the atom. And you can cool it. And let me give you a few examples of mechanisms to cool atoms. And let me start with the simplest possible one, which is called laser Doppler cooling, and which has been invented by these people. The idea for cooling atoms is to take not a single beam, but two laser beams counter-propagating in this direction and in this direction, with the same frequency, the same intensity, the same frequency, new laser, slightly smaller than the atomic frequency between the ground state and the excited state. So what happens? If the atom is at rest, the two laser frequencies are not Doppler shifted, they are the same. They have the same intensity, so the radiation pressure in this direction and the radiation pressure in these directions are equal and opposite. They cancel out, there is no force. If the atom is moving to the right, as indicated here, because of the Doppler effect, the counter-propagating wave will have its apparent frequency shifted up. It was smaller than nu A, it will become closer to nu A, so more photon will be absorbed because you are closer to resonance, so the force will increase. The opposite conclusion holds for the other wave, which gets farther from resonance because of the Doppler effect, and the less photons will be absorbed, the force will be smaller. So because of the Doppler effect, you have the two radiation pressure for no longer balance, and you have a net force opposite to the velocity and proportional to the velocity. This is what in physics you call friction force. It's exactly what you have when you have a pot of honey, and when you try to move a spoon in the pot of honey, the faster you go, the bigger the force. It's a viscous medium. And here you have a viscous medium, except that the light is replaced by, the honey, is replaced by light. This is what people call that scheme optical molasses. It's a molasses where honey is replaced by light. And let me just show you a picture here. I have explained to you how you can cool the atom along this direction. If you add X direction, you had 2 beams along the Y direction, 2 beams along the Z direction, 6 beams. And this ball here is a ball of atoms which are cooled in the 3 direction, an optical molasses. In fact, this is not what happens in the reality. You have other cooling schemes which are much more efficient than Doppler cooling, and one of them was studied in Paris with my young colleague Jean Dalibard, and we call it Sisyphus cooling for reasons which I will explain now. In fact, when you have an atom in the lower state has a structure, because the atoms also are spinning tops. They have an angular momentum. And as in all physical quantities, this angular momentum is quantized. Let me consider, for example, a simple case of what is called in physics spin 1/2. The spin of the atom can take 2 values, spin up or spin down. So you have 2 states in the lower state, spin up and spin down. Now, because you have 2 laser beams counter-propagating, and since they are coherent, you know that laser beams are coherent, they interfere, and you have a standing wave with maxima and minima of intensity. And you can show that in a light beam with a given intensity, the 2 spin states are shifted. They undergo a shift. In fact, that was my PhD work, to what we call light shift. An atomic level in a light beam is shifted by an amount proportional to the light intensity. And since the light intensity is modulated, the shift is modulated. And also, it's not the same for the spin up and the spin down state. So you have specially modulated light shift of the 2 spin states, spin up and spin down. Now, an atom in a spin up state can absorb a photon and fall back, not in the same spin state, but in the other spin state. This is what is called optical pumping, and it was discovered by my thesis supervisor, Alfred Kastler, and he got the Nobel Prize for that in 1966. And because the polarization of the beam is modulated, you have also modulation of the pumping rate from plus to minus and from minus to plus. And you achieve a situation like the one which is represented here, where you have the atoms starting at the 2 levels, which have displacement which are specially modulated. The atom starting from the bottom of a valley climb a potential hill and reaches the top of the hill, where it has a probability to be optically pumped in the other state, that is to say in the bottom of a valley, and again it climbs the hill optically pumped, and so on. And you see that this is exactly the situation of the hero of the Greek mythology, Sisyphus, who was condemned to roll up a rock to the top of a mountain, and when he was at the top, the gods were putting him at the bottom of the mountain. He has to do the job again and again. That's exhausting. And that mechanisms, we have shown that it exists, and this is the best laser cooling mechanism. It can cool atoms in the microkelvin range. It can cool atoms to 10 to the minus 6 Kelvin. Now, since that time, other mechanisms have been also developed for achieving Bose-Einstein condensation, and one of them is very simple. It's called evaporation. And the idea is the following. You have a trap where atoms are trapped, a potential well, and suppose that you have two atoms in the trap with energy E1 and E2, and suppose that these two atoms undergo an elastic collision. After the collision, they have energy E3 and E4, and of course, because of the conservation of energy, E1 plus E2 is equal to E3 plus E4. If E4 is larger than the depth of the potential, the atom with E4 leaves the trap. The remaining atom has an energy E3 which is much smaller, and by colliding with the other atoms and by thermalization, the whole sample cools down. So you lose atoms, you lose the hottest atom, and the remaining atoms are colder. This is exactly what you do when you blow above your cup of coffee. You evacuate the hot molecule, and the coffee cools down. And with this technique, starting from laser-cooled atoms, you can go down to the nano-Kelvin range. So now you can ask the question, why do we work on cold atoms? I would say first, because it's amusing, it's fun. It's fun to try to find mechanisms for cooling, for trapping. And you know, I think that the ludic aspect of research is very important. But they are also very interesting for physical and practical application. And the first class of application is that since they are cold, they move slowly, so you can keep them in the observation zone for a very long time, T. So you can observe for a much longer time than usual atoms which are moving very fast. And in fact, in physics, when you make a measurement on a system, the longer you observe the system, the more precise the measurement you can do. In fact, the resonance line you can obtain on atoms have a width delta nu, which is very often inversely proportional to the observation time. So since you have now very long observation time, you have very narrow resonance, atomic resonance, and you can measure atomic frequency with very high accuracy, and you can lock clocks on the atomic frequencies very accurately, achieving what is called atomic clocks, which are now about 1,000 times more precise than all the clocks which had been performed before. And now atomic clocks using cold atoms have a relative frequency stability and an accuracy which are reaching 10 to the minus 16. What does that mean? To give you an order of magnitude, 10 to the minus 16 means that the clock starting at a certain time, after 300 million years, it will be wrong by less than 1 second. So it's a really precise clock. And then, of course, you can use such clocks for improving the GPS system. And you can also do with this clock test of general relativity. And you can look, for example, which is done now, are fundamental constants of physics varying in time in the cosmological scale. So you can do both basic physics and applied physics. The second big class of application you can use with cold atom is what I will call wave nature of atomic motion. It's due to the fact that at very low temperature, you can no longer consider atoms as point particles, as billiard balls, small billiard balls. They are also waves. That wave-particle duality for matter. So let me explain this a little more, and let me explain to you what is wave-particle duality for atoms. In fact, in 1924, Louis de Broglie introduced the revolutionary idea that it extended to matter the wave-particle duality which was well known for light. It introduced the revolutionary idea that with every matter particle of mass m and velocity v, there is a wave which is associated, which is called now the de Broglie wave, or the wave function, and the wavelength of this wave is given by this formula, lambda de Broglie is equal to 8 Planck constant divided by the product of the mass by the velocity. When you look at this formula, you see that V is at the denominator. So the colder the atom, the smaller V, and the larger lambda de Broglie. That means that cold atoms have very long wavelength and that the wave nature of atoms becomes easier to observe. Let me give you a few orders of magnitude. If you have a temperature 300 Kelvin, room temperature, typically an average velocity is order of 500 meters per second, and for a typical atom, alkali atom, you get a lambda de Broglie on the order of 10 minus 8 centimeter, which is 0.1 nanometer, which is the size of an atom. It's extremely small wavelength. But if you are at 10 nanokelvin, 10 minus 8 Kelvin, the velocity is 1 millimeter per second, and the de Broglie wavelength is 10 micron, which is quite large. Even you can observe this distance at microscope. So you see that at low temperature, the de Broglie wavelength becomes quite appreciable. Now, I'm now ready to introduce the main topic of my talk, which is Bose-Einstein statistics, that Bose and that Einstein. Let me first explain to you how this idea happened. In fact, in 1922 or 23, Einstein received a manuscript of a young Indian physicist, Bose. Bose was trying to derive the statistics of radiation by thermodynamic arguments and by statistical mechanics argument. And in statistical mechanics, what you have to do is you have to count the number of microscopic states associated with a given macroscopic state, defined by the temperature, the total number of particles. Let me take a very simple example. Suppose I have two boxes, the left box and the right box, and suppose we have three particles, and we have to count all the possible way of ranging, putting these three particles in the two boxes. And let me first suppose that the particles can be distinguished. They have labels, 1, 2, 3. You see, you have a single way of putting the three particles in the box, left box, in the right box. If you want to put one particle in the left and two particles in the right box, you have this possibility, 1 here, 2, 3 here, 2 here, 3, 1 here, 3 here, 1, 2 here. You have three possibilities. And you have also three possibilities for putting two particles in the left box and one particle in the right box. And counting all these possibilities for a more complicated problem, you can calculate the entropy of the system and you can make all the statistical mechanics. But Bose considers the fact that very often, in particular for photons, you cannot distinguish the particles. They have no numbers. They are indistinguishable. If the particles are indistinguishable, for example, you have only one possibility to put one particle in the left box and two particles in the right box, because you have no numbers. You cannot label each particle, and you have only this possibility. So you see that the counting is not the same, depending the particles are distinguishable or indistinguishable. And by taking the indistinguishable case, Bose was able to derive very simply Planck's law, which is a basic law for thermal radiation. So Einstein was very much interested by this paper. He helped Bose to publish it. He translated, in fact, the article in German, and he had it published. He didn't sign the paper because it was not his work. But after he thought, why don't we apply this to atoms, not to photons, to the gas of radiation, but to gas of atoms? And he did the work in 1924, and then he predicted a new physical effect, which was very strange. And what is this effect? It's the following one. If you apply the same counting technique to a gas of atom, you find that, suppose that you take n atoms. Let me just add bosonic atoms. I will explain later on what is bosonic, what does that mean, bosonic. Suppose you take n atoms in a trap at temperature T in equilibrium, and suppose that you lower T. And what you find is, when you lower T, of course, the de Broglie wavelength increases. And when T becomes lower than a certain temperature, which is called critical temperature, then the atoms start to go all together in the same state, in the ground state of the trap. You get a macroscopic number of atoms accumulating in the same quantum state of the trap. And since the quantum state is described by the wave function, you have a macroscopic number of atoms in the same wave function. You have a giant matter wave. And in fact, just at the same time, de Broglie was publishing his paper. And Einstein received a copy of this paper by Paul Langevin. And he said that that's very important. I think that de Broglie has opened part of the big curtain of nature. And in fact, when you look at the expression for the critical temperature of the Bose-Einstein condensation, you find that the critical temperature corresponds to a situation where the de Broglie wavelength becomes large enough to be on the order of the mean distance between two atoms, or larger. And I have represented here a pictorial picture of what happened, representing the waves associated with the atoms when you decrease the temperature from a value much larger than the critical temperature to a value lower than the critical temperature. When you are well above the critical temperature, the wavelength is extremely small, so the waves associated with the atoms are negligibly, you can forget about them, you can consider atoms as particles. So that's a classical picture we have on a gas of atoms. When the temperature decreases, but still larger than critical temperature, you start to see the waves, but they are well separated from each other. When you reach the critical temperature, then the waves start to overlap, and as any two waves, they interfere, and they produce an interference effect, which is at the origin of the condensation. And when the temperature is lower than the critical temperature, all particles are in the same wave. And there is a picture which has been published by Science magazine, the year where Bose-Einstein condensation was observed, representing the atoms in the same wave as an army marching in lockstep, all atoms in the same state, exactly synchronous, that the atoms which are condensed, and these atoms here are the atoms which are not yet condensed. Now we can ask, how can we see this effect? How it can be observed experimentally? And the answer is the following one. If you look at the spatial distribution of atoms when the condensation occurs, you expect to see a bimodal distribution, two-peak structure, like that, a large structure and a narrow structure. The narrow structure is the contribution to the spatial distribution of the atoms which are condensed in the ground state of the trap. And the ground state of the trap has a smaller wave function with a smaller width, so they have a narrow position distribution. And the broad pedestal here is the contribution of non-condensed atoms which occupy excited state of the trap with broader wave function. So you expect to see a bimodal distribution. And how can you look at this? That the vessel which contains the cold atoms, you irradiate this atom with a laser beam, a parallel laser beam, and you look at the absorption of the laser beam due to this cloud of cold atoms. So you measure the absorption along a line, and you make a 2D absorption measurement of the optical depth of the cloud along X and Y. And you make the image with the lens of this plane onto a CCD camera, and you get a plot, a 2D plot of the optical depth of the cloud. And this is what you see. That was the first picture obtained by Eric Cornell, Carl Wyman, and in Gila, Boulder, in 1995. You see the 2D picture in false colors above the critical temperature where you have only the thermal cloud. At the critical temperature where you have the thermal cloud and the condensate, the atomic charge condensate, two peak structure, and below the critical temperature you have only the condensate. And that's a similar picture obtained by Wolfgang Ketterle at MIT, showing above the critical temperature, at the critical temperature, and below the critical temperature. And here you have about 1 million atoms, a macroscopic number of atoms, all with the same wave function. And since that time, a lot of other atoms have been condensed, and even molecules, as I will explain later on. Since 1995, a lot of activity has been devoted to this research field. Why? Because we have a lot of phenomena you can study on this fascinating object. You can study what is their shape, how they move, how they vibrate. If you have a drop of water and it can vibrate, is the condensate vibrating? What is the effect of atom-atom interaction on the shape and the dynamics? If you take two condensates, do they interfere? If you take these two giant waves, do they interfere? If you take a condensate and if you make a small hole in the condensate, if you extract atoms from this condensate, do you get something which is equivalent to a laser? In a laser, you have a cavity containing a macroscopic number of atoms, all the photons, all in the same quantum state, and one of the mirrors is not perfect, and what is coming out is the laser beam, which I show here, very directed. Have we the same phenomenon on a condensate? Can we make an atom laser, a laser where optical waves would be replaced by matter waves? And so on. Can we observe superfluidity on such a system? Can we observe a very important phenomenon of solid-state physics, the transition between superfluid and insulator state? Can we make condensate with molecules? You see a lot of questions, and there's a lot of activity. And here I've just represented a few examples of first-page magazines devoted to BEC in all countries. The number of publications on Bose-Einstein condensation, starting from this before the observation of BC to now, is increasing dramatically. And in fact, this research field has been awarded by 2 Nobel Prizes, the field of cold atom, one in 1907 for the development of method to cool and trap atoms with laser light, and one in 2001 for the achievement of BEC, which is quite exceptional to have 2 Nobel Prizes of the same similar research field within a 4 years interval. So let me show you now a few examples of phenomena you can observe. I mentioned to you that the condensate can vibrate. And this is an example of such a vibration. You have a condensate having an anisotropic shape, the shape of a cigar, and you see that the center of mass of this cigar is oscillating. The cigar is oscillating, and at the same time, it's vibrating along this direction. You see it's long here, long, short, and so on. And you can have a full quantitative understanding of this vibration frequency, like a drop of water which you modulate. And in fact, that's also very similar to the vibration of a nucleus. Now, what about interferences? This picture shows you a phenomenon that you are familiar with. If you have two waves on the surface of water coming from two different points, in the place where they overlap, you see maxima and minima, which are called interference fringes. Should we observe the similar effect with two condensates? Experiment of this type has been done at MIT. The experiment is the following one. You take a condensate having the shape of a cigar, you cut it in two parts with a laser beam, and you let the two condensates fall by gravity. They fall, they expand, like that, they overlap, And in the overlap region, the two condensates are together, they interfere, and with the probe laser beam, you look at the structure of the overlap zone, and this is what you observe. This is experimental picture, a more pictorial picture. You see clearly maxima and minima, which means that these two matter waves are coherent. And a lot of experiments have been done, and it has been shown that in the condensate, the phase of the condensate is the same all over the condensate. It's a macroscopic coherent object. Now, I mentioned to you just before an atom laser. This is an example of atom laser. You have here a condensate, a small hole in the condensate where atoms escape and form a beam of atoms, a coherent beam of de Broglie waves, which is as directive as a laser beam, and that's called a laser, atom laser. And that's very promising scheme for atomic interferometry. You can repeat with de Broglie waves all the interference experiments which are well known in optics. And these interferometers using de Broglie waves are very promising because they are potentially much more precise than the optical interferometer. We hope to be able to achieve gyrometers measuring the rotation speed much more sensitive than gyro, laser gyro. Now, superfluidity. It's well known in condensed matter physics, liquid helium, for example, that when you have superfluid helium, what does that mean? It means that if you have superfluid helium, when you take some object in the liquid and you try to move it, if the velocity is smaller than a certain critical velocity, you don't feel any friction. The motion is frictionless. That's what is called superfluidity. Of course, if you go over the critical velocity, then you start to excite in the fluid some excitation and you feel some viscosity. Experiment of this type has been done at MIT, and it has been shown that when you try to move something inside the condensate, if you move it slowly enough, you don't feel any force. It's completely superfluid. Something which is also very impressive is the following thing. That experiment has been done in helium, superfluid helium. Suppose you have a superfluid helium contained in a vessel, a cylindrical vessel, in a bucket, and suppose to start to rotate the bucket. If the angular velocity is small enough, the velocity of the wall with respect to the helium is smaller than the critical velocity, and the liquid helium does not move. It is not taken by the wall, so it remains at rest. But if you go faster and faster, then it starts to rotate with the walls, but it does not rotate as a rigid body. In a rigid body, when you rotate a rigid body around an axis, the velocity of the point of the body increases linearly with the distance from the axis. In a quantum fluid, when you have a rotation, because the velocity is related to the gradient of the wave function, you find that a quantum vortex, the density is zero at the axis of the vortex, and the velocity, instead of increasing linearly with the distance from the axis, decreases as the inverse of the distance. This is what is called a quantum vortex, and that has been observed in superfluid helium and in superconductors. And the same thing has been observed in BEC, in Bose-Einstein condensate. And this is, for example, what has been observed in our group in Paris, that a 2D picture of a condensate, when you rotate it at a velocity, you rotate the trap which contains the condensate, exactly when you rotate the bucket of the helium, superfluid helium. When you rotate the trap at a velocity smaller than omega critical, the condensate remains unchanged. It looks like a mountain here. But when you rotate faster than omega c, then you start to produce a rotation of the superfluid, but it rotates as a quantum vortex, and you get something like a volcano with a zero density in the middle. And if you look from above, that's a picture of what we have observed in Paris. Below the critical velocity, no hole in the center. Above the critical velocity, you get a hole corresponding to a vortex. Then you increase the velocity, you see a regular array of vortices. You get a lattice of vortices, and when you increase, and so on and so on. And that similar experiment done at MIT, where you see also a lot of vortices appearing, a lattice of vortices. And there's a very striking analogy between what we observe here on gaseous Bose-Einstein condensate and what is observed in superconductors and what is known as Abrikosov lattices in type 2 superconductors. So you see we have now in gaseous system and in superconductors structures which are very similar and which are purely quantum structure. Another interesting effect is what I mentioned just before, superfluid mode insulator transition. Suppose that you make a potential, a trapping potential. Suppose that the trapping potential is periodic in space. You do it by interfering two laser beams. And suppose that and you trap a condensate in this periodic potential. If the height of the barrier here is small enough, then the tunnel effect of the de Broglie waves through the barrier is large, and the matter waves is delocalized the whole lattice, over the whole lattice. And you have a coherent matter wave fully delocalized. And all the waves which are contained here are coherent. Suppose that you increase the potential barrier, then the tunnel effect becomes negligible, and the matter waves are localized in each potential well, and they become incoherent with respect to each other. And if you switch off the potential in the two cases, in the first case, the waves coming from the various wells will interfere and give you a Bragg diffraction pattern, like that. Whereas the waves coming from the different wells here are incoherent, and you get only the diffraction pattern of a single wave. And so you see the continuous transition from the current case to the superfluid case to the insulator case. And that has been observed by Emanuel Bloch at Munich. It's a very beautiful experiment where you you observe on a gaseous system exactly what you expect to see in condensed matter, in solid state physics. Now, let me just give you an idea of the evolution of the experiment in this field. An example of cold atom experiment, usually, which takes about a laboratory of 3 to 4 meters. You have tables with optics. It looks complicated, but it's just optics for focusing the laser beams and trapping the atoms, trapping the atom coming from that direction. So that's an experiment that two people can manage. But as always in physics, when you start to find and to become familiar with a given topic, you can miniaturize the equipment. And now you can observe, for example, that an experiment taken from Munich, there's a similar experiment in all these places, you can make now a condensate on a chip of a few. You see here the coin here, you see you can miniaturize everything on a very small structure. And that's very important for future application, because now you can do ultra cold atoms and condensate on a very small structure. In the same way that electronics has changed dramatically, starting from vacuum tube to very small transistor structure. Now, I finish my talk by extending to fermions. And before doing that, I have to come back to what I mentioned just before. What is bosonic atom? In fact, when you do quantum mechanics, you learn that there are two types of particles in nature, bosons and fermions. Bosons have the property that in a given quantum state, you can have as many bosons as you want of the same type. And in fact, they like to be together. The statistics of bosons is such that they like to be together, they aggregate, and this is why you observe BEC, Bose-Einstein condensation. Fermions are individualists. They don't like to be together. When you have a fermion in a given state, you cannot have another fermion. You can at most one fermion in each state. This is what is called Pauli exclusion principle. And in fact, examples of fermions are electrons, protons, neutrons, which you know, Atoms are done are made with electrons, protons, and neutrons. But now, if you have a composite particle, such an atom, depending, this atom has a total number of electrons, protons, neutrons, which is even or odd. If the total number is even, it's a boson. If the total number is odd, it's a fermion. For example, helium-4, you have 2 protons, 2 neutrons, and 2 electrons, 6 particles, 6 fermions, it's a boson. Helium-3, you have 2 protons, 1 neutron, 2 electrons, you have 5 fermions, it's a fermion. So depending on the isotope, you have fermion and boson. And BEC, Bose-Einstein condensation, is observed only with bosons. Now, if you have bosons and fermions in a trap, they have a different behavior. At low temperature, all the bosons are going to the ground state. This is BEC. But if you take fermions, they pile up 1 fermion per level until they reach a maximum energy, which is called the Fermi energy. And the Fermi energy, EF, defines the temperature, TF, by the relation EF equals KB TF, where KB is Boltzmann constant. TF is called the Fermi temperature. And if you succeed to cool the fermionic gas below TF, you get what is called a Fermi degenerate gas. And this has been observed in the laboratory. Many groups are studying very intensively very cold fermionic gas. Now, what is exciting, if you take 2 fermionic atoms, and if they form a pair, a molecule, for example, the total number of electrons, protons, and neutrons in a pair of fermions, when you add 2 odd numbers, you get an even number. So a pair of fermions is a boson. And since it's a boson, starting with a gas of fermions, making some sort of pairing between 2 fermions, you can get a condensation of pairs of fermions. And you get a superfluid phase of pairs of fermions. In fact, in physics, there is a famous example of condensation of pairs of fermions. It's what happens in a metal when the metal becomes superconductor. In a metal, you have electrons, which are fermions, but it can be shown that if you have an electron moving in the crystal, it attracts the ions behind it, an excess of positive charge, which can attract another electron. So through the ion lattice, you can have a small attractive force between 2 electrons, and they can form what is called Cooper pairs. And these Cooper pairs can condense and form a superfluid phase, and this is the explanation which was given by Bardeen, Cooper, and Schiffer for superconductivity. This superfluid phase of electron moves without any friction, and you get something, a current flowing without any resistance. That's the superconductivity, that BCS model for superconductivity. So when people started to cool fermionic atoms, they looked very hard for finding effects which are similar to BCS. And up to now, 2 types of pairs have been produced between fermionic atoms. One pair is the following one. When you have in the interaction potential of 2 atoms, which is like that, like in chemistry, if you have a bound state which is close to the dissociation level, 2 fermionic atoms with opposite spin can fall in this level and form a molecule, a real molecule. And if the density of this molecule is high enough, this molecule can condense and you get a molecular condensate. And I represented here a gas of molecules which condense in a molecular condensate, and several groups in the world now have observed condensate of molecules. But if you have no such a state, but if you have a long distance attractive force between 2 atoms, which also exists, there's the van der Waals force, then 2 atoms at very low temperature can form a long range pair, something which looks like a Cooper pair, but now instead of having 2 electrons, you have 2 atoms with opposite spin. And these Cooper pairs are very delocalized like that. And this Cooper pair can form a condensate. And people have observed recently in MIT, they have observed such a superfluid phase of Cooper pair of atoms. And also, of course, a superfluid phase of this type. So people now have observed this effect. So I think now it's time for me now to conclude. And I would like to conclude by pointing out what is important, why these objects are important. It's because matter waves observed in gaseous Bose-Einstein condensate have properties, fascinating properties, superfluidity, current, which make them very similar to other systems which up to now have been only observed in liquids, like liquid helium, or in solid, like superconductors. But now we observe similar effect in gases. And why is it important? Because we observe this effect now in gaseous systems which are about 100,000 times more dilute than air. That is orders of magnitude more dilute than a liquid or a solid. And in these systems, which are very dilute, the atom-atom interaction are much weaker than in a liquid and a solid, and the statistics of BEC is not obscured by atom-atom interaction. It's much more pure system to study all these effects. And the effect of interaction can be calculated very precisely. And furthermore, something which is fascinating is that by tuning a magnetic field, you can change the long-distance interaction between atoms. You can have a gas where long-distance interactions are attractive, repulsive, or zero. So you have a knob in your experiment, you can turn the knob, and you can change the interaction between atoms. And that's very important because you can vary everything. You can vary the temperature, you can vary the density, and you can vary the interaction. This is what is called Feshbach resonances, and they have been extremely useful for this research field. So it's a big stimulation, a great stimulation for basic research. And we have now, in atomic physics, model system which can be used to deepen our understanding of superfluidity, currents, which is much more difficult to achieve in liquid or solid state physics because of the interaction. And we hope in this way, that people hope now in this way, that, for example, the study of gaseous Bose-Einstein condensation could shed some light on, for example, high TC superconductivity, which is not well clearly understood. So we have a model now in atomic physics for approaching other fields of physics. I like it very much because it's some sort of dialogue between different branches of physics, and even between physics and chemistry and other fields. So to conclude my talk, I would like to say that I hope to have convinced you that our ability to control and to manipulate quantum systems like atoms, molecules, electrons, has dramatically increased during the last few decades. I didn't have time to discuss about electrons and ions, but let me just tell you, for example, that groups like Demel's group, Wineland group, have been able to trap a single electron and to make measurements on a single electron for several months. So we have now a possibility to control, great control of atomic systems. This is opening completely new research field and allows us to ask new questions and to investigate new systems, new states of matter. And it is clear from what I said, for example, the photon momentum, the quantum nature of light, all these developments can be considered as a direct consequences of Einstein's revolutionary ideas. When Einstein introduced in 1905 the idea that light was formed of energy grain, nobody accepted the idea. And it took about 15 years before it was accepted. So the idea of light quantum was rejected by the physics community at this time, but it was revolutionary, and now we have a lot of application of these photons which have a momentum, and this momentum of photon can be used to cool atoms, to trap them, and so on. And also, there's also a revolutionary idea of Einstein. He introduced the idea of stimulated emission, which opened the way to laser lights, and introduced also the idea of BEC, which is very living field now. And finally, there is another idea of Einstein. You know, he was not so happy with quantum mechanics, and he published a paper with Boris Podolsky and Nathan Rosen in the 1930s, showing the intrinsic nature of this quantum correlation. And he was concluding that quantum mechanics was not complete. In fact, he was not right, because these quantum correlations are there, and now they play an important role, but he had the immense merit to attracting attention on this quantum correlation. And now these quantum correlations are extremely important. They now find important applications like quantum cryptography and like quantum information. And that's also a very active field of physics, which will be addressed in another talk of this meeting by Anton Zeilinger and Ignacio Cirac. So I think the legacy of Einstein is very rich, and I think he really introduced ideas which are still very living. Thank you very much for your attention.